Good afternoon, students. In today's lecture in automobile engineering, the topic is power unit. And in the power unit, today's topic, we will be discussing about the various types of pistons that are there in industry that are being used in various vehicles. In the previous lecture, we have already discussed the what is a piston and what are the various parts of a piston, what are the various desirable properties of the various parts of a piston. Okay, so in this today's lecture, we will start with the various types of piston. So in this, the first type of piston that is available is known as the horizontal slot piston. In the diagram, you can see there is a horizontal slot that is parallel to the grooves, the ring grooves. Okay, this slot is provided just below on the skirt area, just below the your oil groove. Okay, so a horizontal slot is cut on the piston on the thrust and non-thrust side. So these grooves they are provided on the thrust and non-thrust side, both sides of the piston, just below the oil control ring. This restricts the overheating of the skirt. So this acts as a dam, and the heat from the top of the piston, it does not move downwards. This slot, it acts as a dam, okay, and it does not allow this heat to flow towards the skirt side of the piston. Okay, and thus this slot, it prevents the unwanted expansion of the piston skirt. So the expansion of the piston skirt is avoided in such case. So if the expansion of the piston skirt does not take place, so then what will happen? The wear of the piston and the cylinder lining because of the expansion of the skirt that can be avoided. So this is your horizontal slot piston. So in this, these horizontal slots, they are cut on the thrust and the non-thrust side of the piston. Next type of piston is your inclined slot piston. Now in this design, the slots are made in the oil ring groove, and these slots end in the inclined slots extending downwards. Now here you can see that this is the bottommost groove in this diagram. This is my oil ring groove. Now in this oil ring groove, this slot is cut inside this body of the piston, and then this after that there is this inclined slot is cut. So this you can see that the inclined slot that is cut on both sides, that is the thrust and the non-thrust side of the piston, and that this slot, this inclined slot, this is cut just where the ring groove is placed inside the piston. Now these slots, they provide again, they provide heat barrier. Okay, so the heat from the top of the piston, it does not move toward the skirt side of the piston, and they act as a heat barrier. So these slots, when there is this empty space comes in, so heat does not flow from this slot and does not go down toward the piston skirt. So again, these inclined slots, they act as a thermal barrier. Next type of piston is the vertical slot or the T slot piston is there. Okay. Now again, these slots are provided, they act as thermal barriers. So in this case, we provide these vertical slot. Either a vertical slot is provided, okay, and or there is this T slot in which there is a combination of horizontal and vertical slot. So a T slot is provided. Again, these T slots, what they do is they act as one is they act as thermal barrier, okay, and second is they does not allow the expansion of the piston skirt. Okay, now these slots they allow the expansion. So the outward expansion of the skirt is not allowed. The piston, these skirts, they, because of the heat, they can expand internally towards this slot. Okay, so that is why these slots allow the piston skirt to expand without increasing the diameter. So the piston skirt does not So we were discussing about the various types of pistons that are available, and the next type is your the vertical or T slot piston. So vertical T slots, they are cut on again the non-thrust side of the piston. Okay, these vertical or T slots are cut on the non-thrust side of the piston. These slots, they allow the piston skirt to expand without increasing the diameter. So this means the skirt does not expand in the outer direction. So the diameter of the skirt does not increase. So this increase in because the material of the skirt, it has to expand. So this slot, it gives the area for the piston to expand inside towards the inside, okay, towards the this slot side of the skirt. So however, this reduces the mechanical strength of now cutting this slot inside the piston. It results in the decrease in the mechanical strength of the piston. Okay, so there are advantages and disadvantages of having such type of slots in the pistons. The next type of piston is your heat dam piston. Now, in this, what happens is a small groove is cut on between the first, that is your the compression piston groove, compression ring groove, and the top land of the piston. Okay. There is this groove that is cut, okay, between the top of the piston and the first groove, that is the compression ring groove. So there is this slot that is cut. Okay. Now this reduces the path. Now what happens is, now this is my cylinder side and this is my piston side. Now there is this groove cut. This is your heat dam. Now what happens is this heat that is coming from the combustion, it moves from this dam and it does not move directly downwards towards the piston rings. Okay. Now this is diverted onto the this right hand side and then it moves downwards into the piston. Okay. Now this reduces the path of heat travel from the piston crown to the skirt. Okay. And the skirt therefore runs cooler. Now this heat does not go directly into the skirt side. It moves inwards towards the core of the piston. Okay. So the piston, this skirt, it does not go overheat. Okay. And the expansion of the this piston skirt can be avoided. Now this dam is provided. The dam, this groove is provided. This groove acts as a heat dam. Okay. So the heat does not go directly towards the skirt side. So it is diverted in between from the dam. So this is your heat dam type of a piston. Next is your taper pistons. Now the crown side being smaller in diameter than the skirt side. So this first diagram is the diagram of the piston. So its bottom diameter is bigger as compared to diameter at the top of the piston. So this is a taper in shape. The piston is taper in shape. So this clearance at the bottom between the cylinder lining and the piston is small, and on the top you can say this distance is more. So this is under cold conditions when the engine is not running. So when the piston is cold, it is taper in shape. Now as the temperature when the piston starts to run, the temperature starts to increase. Now this top portion comes in contact with heat and it heats. This heat is more on the top side. So this top of the piston expands. Okay. Now with the expansion, what happens is the piston diameter at the top increases and it becomes parallel. When it is hot, when the piston is hot, the piston becomes parallel. The taper is removed. The taper is accommodated by the expansion of the piston from the top side of the piston. Okay. Now as the temperature becomes higher towards the crown, that side expands. So the top side expands than the skirt side. So top side expands more as compared to the skirt side, due to which the piston diameter becomes uniform under the running conditions. So under running conditions, the piston diameter becomes uniform. Similarly, there is another type of piston, that is your cam ground piston. Okay. Now the cam ground piston, from the diagram you can see that it is actually a ellipse. The shape of the piston top is elliptical in shape. Okay. So there is this major diameter A, and there is this minor diameter B. So this is the shape when the piston is cooled. Okay, when it is under non-running conditions. Okay, now the minor diameter of the ellipse lies in the direction of the piston pin. So in the direction of the piston pin, the diameter B is there. Okay, that is the minor diameter is there. Okay, now as the piston starts to operate, so here you can see this is cold. When it becomes warm, a little hot, so this diameter B, it starts to expand, and A remains same. Okay, and when it is hot, then this diameter B becomes equal to the minor diameter becomes equal to the major diameter. Okay, so this is your another type of piston, that is cam ground piston. So generally in the same piston, taper and cam ground both are available in the same piston. Okay, so this is your cam ground type of piston. Next type of piston is your wire wound pistons. Now in this type of piston, a steel wire, okay, under tension, it is put between the your piston pin. This is your piston pin and the oil groove. So oil groove and piston pin in between this steel wire under tension, it is inserted. Now this restricts the expansion of the skirt. So this restricts the expansion of the skirt. Okay, so this is the advantage of providing this wire wound piston. Now next type of piston is your special alloy pistons. Now this type of piston example is low X pistons is there. Now in low X piston, the composition becomes 12 to 5% is silicon, 1.5 to 3% is your nickel, about 1% each of magnesium and copper is there. Okay, so low X is the word comes from low expansion. Okay, so this means the piston has lower expansion, thermal expansion is there. Okay, so this means under under high temperatures, the piston does not expand. So that is why they are known as low X or low expansion pistons. In short form, it is known as low X pistons because they are made up of special alloy that comprises of silicon, nickel, magnesium, and copper. So that's why they are special alloy pistons. Next type of piston is your autothermic pistons. Now in the autothermic piston, it contains a low expansion steel insert at the piston pin boss. Now this is your piston pin boss on top. So here you can see that this pin is there. This pin is installed inside. Okay. Now here in this diagram, this is the top view. Okay. So here you can see that these hatched, these are the your four these or autothermic pistons, or the steel inserts are inserted inside the piston. Okay. Now at higher temperature, these piston inserts, because they have low coefficient of thermal expansion, so these does not expand, and they restrict the expansion of the piston also. Okay. Now in the direction perpendicular to the piston pin, there is a corresponding contraction of the piston due to metallic action. Now at higher temperature, this arrangement causes the piston to expand along the piston pin. Okay, so along the piston pin, the piston will expand, but perpendicular to the piston pin, the piston will not expand. Okay, so these autothermic pistons, they are provided with these low expansion steel inserts. Next type of piston is your bimetallic piston. Now this is made up of two materials, that is steel and aluminium. The skirt is formed with the steel material, and aluminium alloy is used to form the head portion. So there are two parts of the piston. The top part, that is the head portion, that comprises of the head of the piston and the grooves for the rings, various rings. This portion is made up of steel. Okay, and this portion is made up of your aluminium alloy, and the bottom portion, that is the skirt portion, is made up of aluminium alloy. Okay. So now the skirt is formed by the steel, and the aluminium alloy cast is made up to form the piston head and the piston pin bosses. Now, as the coefficient of thermal expansion of steel is quite small, okay, the piston will not expand much. Hence, smaller cold clearances can be maintained. So, because the skirt is made up of steel, so steel has lower thermal expansion. So, the expansion of the skirt is restricted because of the steel material. Now, top portion, because it is made up in oval shape, so it is allowed to expand. That is why it is made up of aluminum rod. Okay. Now, by using this two materials, we can restrict the expansion of skirt. So that is why there is this bimetallic piston is there, because it is made up of two metals. Next is your offset piston. Now in this case, you can see that the pin of the piston is not at the center of the piston. It is offset from that piston. Now the piston pin is offset towards the major thrust side. Now this pin is made offset towards the major thrust side of the piston to reduce the piston wear and piston noise due to the piston slapping. Now, by doing the offset, what happens? We avoid the piston slap, and we avoid the wear of the piston and the cylinder lining on the major side or the major thrust side of the piston. Okay. Now, as the position approaches the top dead center during the compression stroke, the offset causes it to tilt slightly, so that the top skirt surface is placed against the minor thrust side, and the bottom skirt surface is placed against the major side. Now here you can see, when the piston is moving in the compressive, the A diagram, you can see the piston is moving upwards. Okay. Now what happens is the piston becomes tilted. So the top of the piston touches the minor thrust side, and the bottom of the skirt, left corner of the skirt, it touches the major thrust side. Okay. Now when during the minor thrust side, because the thrust is minor, smaller, so the wear is small. Okay, but during the power stroke, after the power stroke, because lot of power, lot of energy is produced, okay, on the top of the piston. Now, when the piston moves in the downward direction from the top dead center toward the bottom dead center, okay, because the piston is offset, the pin of the piston is offset. What it does is this tilt is avoided of the piston, and the piston, you can see that the piston is aligned parallel. There is no tilt that was there during the compression stroke. Now after the power stroke, the tilt is avoided. Okay, now the piston is smoothly in line with the cylinder lining, and the piston slap is avoided. Okay, now this piston slap is a major reason for this wear of the piston and the cylinder lining. Okay. So this is your offset piston here. Next type of piston is your inserted ring carrier piston. Now in this case, you can see that this ring carrier, there it is inserted. It is a separate. It is made separately, and then it is inserted inside the main body of the piston. Okay. Now special ring inserts made of authentic form of cast iron. They are used to resist the corrosive action of sulfur dioxide, sulfur trioxide, and water, the products of combustion. Okay. Now, because when these piston rings they come in contact with these acids like sulfur dioxide and sulfur trioxide and water also, now the corrosion takes place. Now these inserts, what they do is they act as a barrier, because they are made up of authentic form of cast iron. Okay, and they have and they, what they do is they do not react with these sulfurs, and they provide a corrosive resistant layer on the piston. Okay. Now, as the coefficient of thermal expansion of authentic iron and aluminum alloy are nearly the same, the ring insert do not work loose. Okay. Now when they are under working conditions at higher temperatures, because the thermal expansion of both the materials is same. Okay. So there is no problem in working. because they expand equally. So this is your inserts. Okay. Now when these inserts they wear out, these inserts can be changed after if they wear out. Okay. So this is your inserted ring carrier piston. Next is your oil cooled piston. Now in the oil cooled piston, you can see that this is internal groove is cut during the casting of the piston. Now in this internal groove, you can see here. From the you can see from the connecting rod, okay, internal from the connecting rod and through the pin, the oil can flow, and this oil comes inside this groove of the piston, and it acts as a coolant. So this keeps the piston under working conditions and does not allow the overheating of the piston. So a cavity is provided underneath the piston crown to reduce the piston temperatures at the top ring to prevent the formation of carbon in the groove and to achieve sufficient oil film thickness on the ring periphery. Now this type of piston is provided in the medium and heavy diesel engines. So medium and heavy diesel engines, they have internal grooves, because in medium and heavy diesel engines, the heat produced is very high. So this oil, when it circulates through these grooves, it absorbs that heat and keeps the piston cool. Next type of piston is your cast steel pistons. The pistons, they are cast from an alloy steel that contains silicon and copper with cadmium plating and have been found to be highly wear and heat resistant. Okay. So these type of pistons that are made up of cast steel, they are highly wear resistant and they are highly thermal resistant also. Next is your anodized pistons. Now anodizing, it provides a the bearing properties to the piston. Okay. In this, what we do is it is done by we dip the piston in sulfuric acid bath. Okay, and in the sulfuric acid bath, a small or a micro coating is dark colored micro coating is attained on the top surface of the piston. Now this coating, due to this sulfuric acid, because sulfur it enters the surface, now it makes the piston hard. The surface becomes hard, and it prevents the piston from grooving and scoring. Okay, so this is your anodized piston. Next is your tinned piston. Now in this, what happens is there is a small 0.007 mm thickness deposit of tin material is done on the surface coating. The surface coating is done with the tin. The thickness is 0.007 mm. Now this thickness, it acts as a lubrication. The top surface acts as a lubrication during starting, because when the piston is started from the initial, say, when the engine is started, okay, now at that stage, the lubrication is not done. The lubricant does not reach the piston and the cylinder. Now in that case, to avoid the wear of the piston rings and the piston lining, this tin coating, it acts as a lubricant during that. Now that avoids the wearing of the piston. Next is your squeeze cast piston. Now in this case, what we do is we use the squeeze casting operation, in which the material is squeezed and then in that case, under high pressure, the casting is done. And under high pressure, when the casting is done under high pressure, so in that case, what happens is the micro porosity, if there is any porosity, because in normal casting, what the defect of porosity comes in. Okay. Porosity is the small voids or air voids or vents that are there inside the material. Now, under high pressure, these vents can be eliminated or voids can be eliminated, and this increases the fatigue strength of the material. So squeeze casting is applied in which the casting is done under high pressure. Next type of piston is your econo-guide pistons. Now, this is a patented method that is developed by Wellworthy Limited, the company, US-based company is there. They have developed this type of piston. Now, it consists of raised pads. On the skirt, you can see that these are the raised pads. So this is the front view and this is the top view. So you can see that these pads are avoided or these provided, and these are a little raised from the surface of the skirt. Okay. Now these pads, only this area comes in contact with the cylinder lining, okay, and not the whole skirt. So these are specially shaped to assist the creation of hydrodynamic lubrication. By this method, up to 75% of the skirt contact area can be reduced. So the contact area of the skirt or the piston with the cylinder lining, it is reduced by 75%. Now, if the 75% contact area is reduced, this means we have reduced the friction also. So, okay, so this means less losses are there. So only these, you can see that on these pads, there is a small hatched rectangular area. Okay, now these only hatched rectangular areas, they come in contact with the cylinder line when the piston moves. So this means the contact area between the piston and the cylinder lining, it is reduced. And by reducing that, we can reduce the frictional losses. Okay. So this is your econo-guide type of piston. Okay, next is the various engine parameters that are associated with the IC engine. The first is what is the indicated power. Okay. Now the indicated power is the power developed inside the combustion chamber. Now when the fuel ignites, the combustion of fuel takes place. Now the actual power that is being generated inside the combustion chamber, that is known as the indicated power, and it is given by this formula PM, where PM is your the mean effective pressure into L into A. L is your stroke length, A is the cross sectional area, and N is the your RPM there, divided by 60,000 into 2 is there. So this is the formula to calculate the indicated power, and then comes is your the brake horsepower is there, or the brake power. Now this is the power that is available at the crankshaft. Okay. Now it is given by 2 pi n t. T is the torque divided by 60,000. Now this torque can be written in terms of PMB. So here the term comes is PMB. So this is your mean brake effective pressure is there. So this is your PMB into LAN upon 60,000 is there. So this is how you calculate brake power. Okay. Next come is what is the mechanical efficiency. Now this is the indicated power is the power that is developed inside the combustion chamber, and brake power is the power that is available at the crankshaft. Now the difference between the indicated power minus the brake power is known as the frictional power. Now that is the power that is lost because of frictional effects, because there is friction between the piston and the cylinder lining. There is friction between the connecting rod and the piston, and the connecting rod where it is connected at the piston side, and the connecting rod that is connected to at the crank side also. And then the bearings on which the crankshaft is housed. Okay, so those bearings also, in the bearings also the power is lost. So that is the frictional loss. So indicated power minus that friction power, it gives me the brake power. Next is your mechanical efficiency. So mechanical efficiency is nothing but it is the ratio of the brake power divided by the indicated power. Okay. So that gives me the mechanical efficiency. Now most engines, they are 94% mechanical efficient. That is 6% of the energy is lost due to friction inside the engine. Okay, this is your mechanical efficiency. Next comes is your what is indicated thermal efficiency. Okay. Now this indicated thermal efficiency, it is the ratio of the indicated power and the energy in the fuel per second. Now this indicated thermal efficiency is, it will be given by indicated power divided by the energy in the fuel. Energy in the fuel will be mass flow rate of the fuel, how much mass of fuel is entering the combustion chamber minus the calorific value. CV is the calorific value of fuel. So indicated power divided by mass flow rate of the fuel into the calorific value will give me the indicated thermal efficiency. Next is what is brake thermal efficiency. Now in brake thermal efficiency, it is the ratio of brake power to the energy that is available with the fuel. So this brake thermal efficiency is brake power divided by the energy with the fuel is mass flow rate multiplied by the calorific value of the fuel. Next term that is associated with the IC engine is your what is specific fuel consumption, or in short it is known as SFC. Now it is defined as the fuel consumption per unit time per unit power produced. So how much fuel is being consumed by the engine per unit time per unit power produced. Okay, so it is given by how much fuel is consumed is given by mass flow rate. Mass flow rate divided by the brake power of the engine. This will give me the specific fuel consumption of the engine. It is denoted by kilograms per kilowatt hour. So this is your specific fuel consumption. Next, if you see this diagram here, you can see that this is the engine performance curve is there. In this, the various parameters that are being studied are studied on y-axis. You can see the efficiency is there. It is starting from 0 to 100%. Okay, and at the bottom you have the value of capital M, that is RPM, or the engine speed is there. It is starting from 1000 RPM to 2000 to it is going till 6000 RPM. And between these variables, between these RPMs, so as the RPM of the engine is increasing, how the efficiencies, different efficiencies, they are changing. So first, if we see at the mechanical efficiency, so mechanical efficiency is greater when the RPM are less. So here you can see it is around 90%. Okay, when the RPMs are just near 1000 RPM. Now, as the RPMs they increase, okay, so the mechanical efficiency of the engine it starts to decrease. Okay. So here at around 5500 RPM, you can see that the mechanical efficiency has reduced to 70%. So this means as the velocity or the RPMs they are increasing, the frictional losses are more. Okay, so this means that the mechanical efficiency of the engine it decreases with the increase in RPM of the engine. Okay, now this is because as the RPM they are increasing, the heat produced is increasing. Now with that production in heat, what is happening is the lubricating layer is being depleted. Okay, and the lubricant is not performing properly, and with that what is happening, more friction is being produced between the piston and the cylinder lining, and that is why more frictional loss is taking place. So that's the main reason why the mechanical efficiency is decreasing with increase in your engine speed. Now next comes is your what is specific fuel consumption. So specific fuel consumption is greater when the RPM is less. So it is around 81%. Now as the RPMs are increased, the specific fuel consumption starts to decrease. Okay, and around 3500 RPM, after that beyond 3500 RPM, you can see that the specific fuel consumption it starts to increase again. Okay, so here on the right hand side you can see this graph is there. In here you can see that 200, this is grams per brake horsepower hour is there. So at around say 1000 or 1100 1200 RPM, you can see that specific fuel consumption is around 350. Okay, so it is more than 350. So as so 350 gram per brake horsepower per hour. So it is This is the specific fuel consumption. Now, as the RPM is increased and it reaches around 3500, the specific fuel consumption is between 200 and 250. So it is reduced. And again, beyond 3500 RPM, the specific fuel consumption starts to increase. So this is how the specific fuel consumption graph varies with the RPM. Next comes is your what is indicated thermal efficiency. Now, indicated thermal efficiency, this is the efficiency that is associated with the power produced in the combustion chamber. Indicated thermal efficiency. Now, here you can see that around 1000 RPM for the idle speed, the efficiency is less, below 20%, and as the RPM increases, this thermal efficiency, indicated thermal efficiency, starts to increase, and around 4000, if it reaches its peak, say 4200, I think you can say that. So after 4200, there is a small dip, so it starts to decrease. So this is how the indicated thermal efficiency, it varies with RPM. Then similarly, the graph for brake thermal efficiency, it is less around the idle condition, and as the RPM starts to increase, it starts to increase, and around 3200 RPM, it reaches maximum possible value, and after that it starts to decrease as we increase the RPM. So this is your basic engine performance curve that correlates the various types of efficiencies and specific fuel consumption depending upon the RPM. Next graph is about the torque and versus speed and the brake power. Yeah. So here you can see that on the left hand side we have the power in terms of kilowatts. So it is varying in the variations of 5. So it starts from 10 kilowatt, 15, 20, and goes up to 70 kilowatt. At the bottom, you have the RPMs starting from 1000 RPM to 6000 RPM. Okay. And then you can see that there are various values of, it starts from on the right hand side, you can see there is specific fuel consumption. It varies from 0.25 to 0.4. It is in terms of kilograms per kilowatt hour. Then is your brake mean effective pressure is there. Okay. So it is starting from 800 kilonewtons per meter square. It goes up to 1000 kilonewtons. Then is your torque, Newton meter. It starts from 110, it goes to 150. So here you can see that the torque, it is a good indicator of the ability of an engine to do work. So the more the torque that is available at the wheels, the more load the vehicle can carry. So that is why the torque for the motor cars or bikes is less, okay, and the torque for the trucks and trains and buses is more, because they can carry more load. Okay. Now the torque and the speed of any vehicle, it is inverse in proportion. Okay. Now if a vehicle has more torque, it will have lesser speed. So if you have more speed, so you will have lesser torque. So that is why the cars, they can run at higher speed because they have lesser torque, okay, but they can run at higher speeds. But trucks, on the other hand, they have higher torque. They can pull more load, but they cannot move at a higher velocity. Okay. Similarly, the tractors are there. Tractors, what they do, they have higher torque is there, but the top speed of the tractors is very less. So there is a inverse relation between torque and speed of a vehicle. So torque is defined as the force acting at a moment, distance, and has its units as Newton meter. Okay. So many modern automobile engines have the maximum torque in the range of 150 to 200 Newton meter within the speed range of 3000 to 4000 RPM. Now here in this graph, you can see for this particular type of vehicle. Now when at 1000 RPM, the torque is around, say, you can see here the torque is around 120 Newton meter is there. Okay. Now, as we increase the RPM, the value of torque it increases, and at this point, where it is around 300 or 3200 RPM, it becomes maximum to 150 Newton meter, and beyond this 3200 mark RPM, the value of torque starts to decrease. Okay, so torque variation is there, and this you can see this line in between. This is your power line. So power is there. So at 1000 RPM, the power produced is less. Okay, it is around 12 or 13 kilowatt. And as the RPM increases, the power starts to increase, and it reaches the peak at around say 5600 RPM or 5700 RPM. And after that, there is a small dip in the power produced. So this is how the power varies. And then is your you can say here brake mean effective pressure MEP. Again, this is there is low and low RPM, and it reaches to a maximum value at around 3200 RPM, and after that it starts to decrease. Okay. Then specific fuel consumption, it is more at 1000 RPM. It becomes minimum at around 3000 RPM, and after that it starts to increase again if we increase the RPM of the engine. So this is how the various parameters like torque, speed, power, and specific fuel consumption, they vary in an IC engine. Now here in this graph, you can see we have two graphs here. The left graph, it is for a petrol engine. Okay, so here we have two parameters. On the x-axis we have brake horsepower, and on the y-axis we have percentage of energy is there. So total energy that is being produced, that is the indicated power that is being produced inside the combustion chamber, how that energy is consumed in an automobile. Okay, so here you can see that in an IC engine, it is a petrol engine. First we will go for the petrol engine. Okay, so in this you can see that this bottom up to this graph is the useful work. So as the brake horsepower is increasing from say 0 towards, we are going towards 25. So the value of this brake horsepower is increasing. So this brake horsepower from this 0 point, so you can see that around this value, the bottom, the area or the distance below this graph, it gives us the value of the useful power that is available at the crankshaft. So this is the value of, so it is less at lower brake power. Okay, and as we increase the brake power, it starts to increase. So useful work starts to increase. Now above this graph, you can see that this is the graph for the how much heat is being taken away by the coolant from the engine. Okay, so at the start, when the coolant is engine is cold, so the heat taken away by the coolant is more, and as the engine starts to work under working conditions, this energy taken away by the coolant, it starts to reduce. Okay, because more power is available for in useful work region. Okay, next comes is your how much energy is getting okay, so this is how much heat is being carried away by the coolant in the radiator. After that, you can see above this line, the above portion is how much heat is being carried away by the exhaust gases. The gases there that are going out from the exhaust pipe. So it remains around. So you can see it remains around constant. And after say around 20 or say 16 or 17 horsepower, the exhaust heat starts to increase. Okay, and then the rest of the energy loss is through radiation heat transfer. So it is less at a lower brake power, and as the engine speed starts to increase or the engine power starts to increase, the radiation heat transfer starts to increase. So this is how the variation of various heats this is the total 100% is the energy that is available inside the combustion chamber when the fuel ignites, and this is the indicated power. So 100% is the indicated power. Now that indicated power, so some of that energy we use the energy that is available for useful work. This is your brake power. So that is the percentage of energy that is available here for useful work. Then some part of that indicated power is taken away, heat is taken away by the coolant, some goes as waste in the exhaust, and some is lost in the radiation. So similarly, similar graph is available for the your diesel engine or the compression ignition CI engines here. So in this case, you can see that under normal, so this engine is working under 1200 RPM. Okay, so useful work here is more. In the case of diesel engine, this brake horsepower is more. Useful work, that is more. The energy taken away by the coolant is less compared to the petrol engine. Exhaust gases, they have the maximum share. So heat lost in the exhaust gases is more, and radiation is less. Okay. So we have more heat loss in the exhaust, but we have more heat that is available as useful work or the brake power in diesel engine. So that is why diesel engines, they have more power or more torque capacity is there. So more work power, doing work capacity is more in diesel engines as compared to petrol engines. So this is another graph that correlates the heat balance versus the load for petrol and diesel engine.